welcome back. It's part 2 of our lecture about the oceans and the cryosphere. So now let's go on and talk about the cryosphere. Hey, you might not be familiar with that word cryosphere, but it's no big deal. It's basically just the frozen water part of the Earth's system. Okay, we're talking things like sea ice and ice sheets and glaciers and things like that. And so let's actually talk about them each kind of separately. Let's talk about glaciers first. Now, well, gosh, I mean, everybody on Facebook knows about... What do I know about Facebook? I don't do Facebook. Everybody on Facebook knows that glaciers are melting, right? We've all seen the pictures of the glaciers retreating, you know, getting shorter. We have all heard from our skeptical uncle who says that they're not, blah, blah, blah. And it would make sense that if the world is getting warmer, there should be fewer glaciers. Or maybe smaller glaciers. Or maybe glaciers that are less thick. Or, I'm making a point here. I'm not sure what would make sense, okay? I'm not sure what to expect. Should glaciers be gone if the world is warmer? Should there be shorter glaciers, thinner glaciers? Let's see if a definition of glacier would help. I got this from the Dessler textbook, which we use in a different class. And that class said glaciers are going to be forming when there's cold regions where the snow falls in the winter and does not completely melt back the subsequent summer. Okay, that makes sense. We are accumulating snow. We gain more snow in the winter than we melt in the summer, and we accumulate this snow, making it then under its own weight compact into a state of ice that is, can flow down a hill and things like that. Now, as it happens, some years ago, I got a chance to go to a glacier. And I'll show you some pictures from this vacation. This was, oh gosh, quite a few years ago now, maybe almost 10 years ago now. But my wife and I took a trip to the Canadian Rockies, and one of the places you can go is to the Columbia Ice Field, which is very near the hydrologic triple point up in Alberta someplace, and it's a very high it's an ice field with glaciers coming down from it. And here I am, and much to our surprise, I don't know, we didn't research it very well. We weren't there to see glaciers. We were actually there for a broader trip. We were actually having a nice vacation and taking pictures of wildflowers. It was June, and we went to the glaciers as well. And what we didn't know is you actually get to ride a vehicle out to the ice. And actually, you don't just take pictures from a distance. You get to go walk on the glacier, which I don't really like the idea of. I don't really like the idea that people are walking on glaciers. They have crevasses. They have, your feet are tracking dirt onto the glaciers that changes the albedo of the glacier. I'm not happy with that. But of course I did it because I paid my admission. So you get onto a little vehicle called the Ice Explorer, and you go up and you see these lovely mountain glaciers. See how like there's a glacier coming down this valley here? Oh, coming down the valley. It's making the valley, right? It's carving the valley as it comes down, and you can see it's quite thick, you know, it's quite lovely here. And some of the vehicles that they take out there are horrifyingly bad. I mean, again, by the way, this is June, so most of the seasonal snowfall is gone. But I mean, there's a beat-up old piece of crap vehicle that they use on their snow tours there, and you go up the valley, up towards the ice fields. Now, the true ice field that's way up high, up in the top of the ridge up there, you can't quite get to, but you can see this big old glacier coming down there, and it's all very lovely, and you get to see how all this, and of course the tour guide is telling you how glaciers form, and the tour guide is telling you about how global warming means that, well, they're going to say the glaciers are retreating, but I don't know, maybe that just means that fewer glaciers are forming, or maybe that means... I'm not sure yet. I'm not sure what the answer is. And then, horrifyingly, they take you actually onto the glacier itself, including driving the vehicle with its dirty tires out onto the glacier. And you can see how people are tracking dirt onto the glacier, which when the sun shines on the glacier now, the sunlight will be warmed by the brown dirt, and you'll melt the glacier even faster, and the whole thing is frankly kind of horrifying to me. But we did it because we had paid our admission and whatever, anyway, I guess that's what everybody feels. But anyway, I had never been to a glacier before. I was pretty excited that we got to go on that vacation to a glacier. And, okay, I feel like we learned something here. Well, as the tour guide mentioned, glaciers seem to be getting shorter, and in fact, measuring the length of a glacier is pretty easy. I mean, it's pretty easy to know where the ice field that is sort of the uphill part of the glacier is, and it's quite clearly defined where the end of the glacier is. There's usually, you know, a line where it's ice over here and it's dirt over here, so it's pretty straightforward to tell the end. Measuring the length of a glacier is pretty straightforward. And all glaciers are monitored by climatologists and state agriculture people and so on. All of them are monitored down from space as well. And one of the things we know is that all glaciers all around the world are getting shorter. Okay, I just said something that's not quite right. Yes, obviously there exists glaciers that are getting longer, but average over all regions of the world, average over all of the individual areas where there are glaciers, like the Alps or the Southern Hemisphere or Asia or whatever, we aren't finding any parts of the world where glaciers aren't getting shorter. So, again, this is just sort of length relative to their 1950 length. They're defined to be 0 in 1950. So they were about an average of about 1.5 kilometers longer, you know, if you go back a couple hundred years, and they're about 500 meters shorter if you moved then forward to the present time. By the way, yeah, we can go all the way back to like the 1700s in these measurements here. Okay, clearly in some parts of the world we have been measuring the lengths of glaciers for a very long time. Sometimes they can reconstruct the length of glaciers from things like paintings. When people painted a painting of the mountains, they generally won't have taken artistic liberties to, like, you know, vastly changing the length of the glacier or something like that. There are ways to recover this information from old photographs and so on, all of which makes it relatively easy to have good documentation about the length of the glacier. But the truth of the matter is that is not exactly the same thing as saying the warming of the world is causing that. Because temperature is not by any means the only factor that affects the length of a glacier. I mean, glaciers are a complicated balance between the amount of snow falling up in the ice field down at the top of the mountain, where it's definitely cold enough, even with global warming, that we are getting lots of snow. In fact, maybe we're getting more snow because of global warming, like the atmosphere can hold more water vapor and so on. And then that has to be balanced by how much melting is happening at the lower altitudes on the glacier, which might be related to global warming, all of which could be affected by changes in the amount of precipitation the region is seeing, all of which could be affected by the rate, by how cloudy a region is. I mean, we said we can't really find any global changes in cloudiness, but that doesn't mean that there aren't changes in regions. This makes me uncomfortable. I definitely think glaciers are getting shorter, but and don't get me wrong, from a personal point of view, I suspect it is the temperature changes, but I get it from a scientific point of view, this is hard to prove. But there is a key piece of evidence here. Since, if you look at this diagram here, since the observed glacial retreat is global, since all parts of the world have about the same amount of change in the length of the glaciers, the cause is apparently global too. If there were different factors causing the changes in the length of the glaciers in the Alps versus the length of the glaciers in the Himalayas, we wouldn't expect them to have about the same amount that they have retreated, right? I mean, it would be a very strange coincidence if glaciers in the Alps had retreated by 1 kilometer and the glaciers in the Himalayas had retreated by 1 kilometer, but they were for very different reasons. It could happen, but that would make a scientist scratch his head and say, I don't know that I believe that. And when you start seeing other parts of the world too, then it starts becoming very unlikely that this is about regional differences, like changes in cloud cover or something, versus it's a global impact due to like the global change in temperatures due to global warming. I mean, we have no evidence of a global change in precipitation. We think that there ought to be, but we don't actually have evidence of that. We don't have global evidence of changes in cloud cover. It seems that there ought to be, but there isn't. Observations don't show it, so what we do have a global evidence of is global changes in temperature. Makes it very likely that the observed retreat of the glaciers is associated with changes in global mean temperature, which makes perfectly good sense. The tour guide on the ice tour was right. Or ish, right-ish. Let's talk about sea ice, where the surface of the ocean has actually frozen into a layer of ice at the top of the ocean. This will only happen in places that are really, really cold. The ocean, of course, in general, has a very high heat capacity. Once you start freezing the top of it, the water below the surface is no longer in contact with the bitterly cold air. You only get something like a meter or two thick layer of ice, of this seasonal sea ice. And a very large amount of the Earth's surface is covered by seasonal sea ice, with a very large annual cycle that we do a great job monitoring using satellites. I mean, you can go to the brilliantly named National Snow and Ice Data Center, and on any given day find out exactly how much sea ice there is in the Arctic, or at least how much they estimate from their remote sensing techniques and so on. So like, this happened to be, I think I was using like 2014 data or something like that when I was playing with their website. But like that panel on the left was like the March 2014 sea ice and the September 2014 on the right. It might have been 15, it doesn't really matter. The red line on there is like the average sea ice extent on that in March, and the red was like the average on the September one. That is the average in September. And what you see on these diagrams, if you actually look through a whole bunch of them, is that in general, the problem isn't usually the sea ice extent in the winter. In the winter, where peak sea ice coverage is about March, because all through from September to March in the Arctic, the sun isn't even up, right? They have 6 months of darkness. It gets really, really cold. In the winter, the temperatures are just so far below the freezing point that a little bit of warming doesn't make the temperature sufficiently close to melting that all that much ice melts. So the wintertime sea ice extent tends to be, even in the presence of global warming, tends to be fairly close to the long-term average. The situation is very different in September. Now, the Arctic regions have been under 6 months of sunlight. The temperatures in the Arctic in the summer are right around the freezing melting point. A little bit warmer tips the balance toward melting, right? I mean, if the temperatures at these locations tends to be around 28 degrees Fahrenheit, maybe 35 degrees Fahrenheit, maybe 31 degree Fahrenheit, a little bit of warming is the difference between melting and freezing. So a little bit of warming in the summer results in a whole lot of difference in the sea ice extent. And that's bad. So like if we use September sea ice extent as sort of our metric of how much warming has been happening at the Arctic, well, if we just look at like, this is satellite remote sensing observations since 1979, and you can see this very bad trend. You can see, by the way, these are not anomalies, this is absolute. So like, in the late 70s we were seeing about 7.5 million square kilometers of sea ice, and now we see more like 5 million or less in the winter. That's a big decrease in the total sea ice extent. Actually, it's all horrible. This happens to be a diagram I pulled off in January of 2017 off of the National Snow and Ice Data Center's website, where they're showing data about sea ice extent on a daily basis. The blue curve is the 2016-2017 winter. So you can see that in like September of 2016, we had only about 4 million square kilometers of sea ice coverage in the Arctic. And as it got darker and it got cold in October, November, December, the sea ice expanded. And that all sounds good until you notice the black curve, which is the long-term average. You can see we're nowhere near the long-term average amount of sea ice in the Arctic. And in fact, the gray area around that black curve is showing us plus or minus 2 standard deviations. We're more than 2 standard deviations away from the average, okay? This is a very anomalous amount of sea ice. In fact, you can actually use their website and play it and show things. This is actually a track for all, whatever it is, 40 years or whatever of sea ice data that they have from the satellites. And so each colored line on there is 1 year's annual cycle of sea ice coverage, where it peaked in about March and minimum sea ice in about September. And if you look starting at about October and farther to the right, see how one curve is very different than all the rest of them? Let me zoom in on that. That red curve that is very different from all of the other curves, that's fall of 2016. Something is very strange. Even in the presence of global warming, something strange is happening in the Arctic in fall 2016 and winter 2017. We have way, way, way too little ice in the Arctic. In fact, you can see a little dip right there, kind of in the middle of the graph right there. There was actually a period of time this winter where, despite the fact it was dark, sea ice extent was actually decreasing. Ice was melting in the Arctic. Something is very wrong in the Arctic this year. Now, we like to use sea ice extent as sort of an indicator of climate change. That was way back in like the second lecture of this course. We made a list of climate change indicators, something that would be a marker, that would be evidence of climate change. But actually, sea ice is not just an indicator of climate change, it's actually kind of part of the story of climate change. Sea ice is like a blanket that separates the, well, relatively warm Arctic Ocean from the bitterly cold air. The sea ice is part of the story of the climate itself. The sea ice is a blanket that separates very, very cold air from relatively warm ocean. I mean, the ocean can't be colder than like 32 degrees Fahrenheit, right? If it was colder than that, it'd freeze. So, alright, so like here's a nice picture. Look at the background here. We have a fairly continuous sheet of sea ice here. The air above the water is probably very, very cold. -20, -30, -40 degrees. But the water below is much colder, warmer than that. Probably right around 0 degrees Celsius, 32 degrees Fahrenheit. But the sea ice is keeping the ocean from warming the air. There's no conduction of heat from that warm source of heat, namely the sea ocean, from the cold air. There's a scientific piece of jargon here. The right word for this is sensible heat flux. This is what in intro we called conduction. There is a flux, a transfer of heat from the ocean into the atmosphere. Sensible heat, not as in it's sensible like it uses common sense, sensible as in it can be measured with thermometers. And the sensible heat flux in this situation is quite low because the ice is acting like a blanket. Well, what happens when the ice is broken up into these leads and polynyas? Hey, there's some vocabulary words I don't even have on there. Leads and polynyas are the cracks and the kind of ponds that form between the pieces of the ice flow. I wouldn't have the word leads and polynyas on there on the quiz or the test or anything like that, but that's what those things are called. But once it's all broken up like that, without that sea ice coverage, the heat conducts very easily from the warm, the scaldingly hot water compared to the air. I mean, the difference between the air temperature and the water temperature might be, you know, 20, 30 degrees Fahrenheit. I'm sorry, 20, 30 degrees Celsius. Now the sensible heat flux is high. The water is so warm compared to the air, there's a huge transfer of heat up into the atmosphere once it's broken up. Notice that this leads to a feedback. I mean, if a warmer planet means that there's less sea ice means that there's warmer air over the Arctic. This is part of the story of why the temperatures have increased so much over the Arctic compared to other parts of the world. Now, there's also going to be the ice albedo feedback, which is part of the story too, but this feedback is part of the story. Rats. The situation with sea ice is not good. Let's talk about ice sheets. Now, ice sheets are different from sea ice. I know that, like, on a Discovery Channel documentary, they might use the words kind of interchangeably, but ice sheets are on land. And in fact, at this time in Earth's history, there's really only two ice sheets. That is to say, the Antarctic ice sheet and the Greenland ice sheet. Obviously, like in the most recent ice age, there were ice sheets across Canada and the northern United States, etc., but those are gone. At the present time under Earth's history, there's only two ice sheets, but they both have a very large mass, and if they're large, and they are well above sea level. You know, the ice sheet in Antarctica is several kilometers thick. If we melted all of Antarctica and Greenland, the sea level would increase by like 100 meters. Now, is that going to happen? No. Well, certainly not on time scales that like you and I will experience, okay? There are possibilities that like the Antarctic ice sheet maybe have become unstable and is falling apart, but even really scary scenarios on that, we're talking on the order of hundreds of years before, you know, there would be a major breakup of the ice sheet. But no matter what, I mean, we're also going to have global warming for hundreds of years. We're going to learn more about committed warming later in the course. But, I mean, the Antarctic ice sheet breaking up over the course of the next 400 years is a real possibility, and we certainly will have global warming for that long. These ice sheets are in big trouble. I don't think I needed to tell you that. We have lots of ways of measuring them. Like, here's the mass of the Greenland ice sheet. Now, this is, again, it has been changed to an anomaly, but I don't think we have any trouble over the course of the last, like, 6 years seeing a trend here. Right? There's clearly an annual cycle to the mass of the Greenland ice sheet. Obviously, it accumulates mass in the winter when it's colder, and it loses mass in the summer due to melting. And wait a minute, how are we doing this? And why we only got like 6 years of data in this particular diagram? What's going on here? Well, actually, how we measure this is really cool. The Greenland ice sheet and the Antarctic ice sheet too are so big. They actually affect the Earth's gravitational field. We can actually measure the mass of the Greenland ice sheet and the Antarctic ice sheet using satellites in orbit by measuring tiny changes in their orbit as they pass over the Greenland ice sheet. If the Earth were a perfectly round sphere made of just all the same material, we know exactly how the satellites would orbit. But because they pass over things like a several kilometer thick sheet of ice that's heavy and massive and weighs many, many, many billions of gigatons and all that kind of stuff, the orbit slightly changes. And if we can measure that, we can actually determine the mass of the ice sheet. We in fact do that kind of gravity recovery and mapping lots of times. That's also how they can do things like measure the mass of water in a reservoir, and there's all kinds of things they can do with this. I mean, it's an astonishing technology. But we can measure the mass of these ice sheets and we can tell that they are melting. And so were the sea ice, and so were the glaciers. And you know what? Above all, it's this consistency between all the different sources of information that gives us confidence that there's something real going on in the cryosphere. Again, it's not the kind of thing, too, that you can pick apart. It's a classic intellectual failure to, like, find a problem with with one part of the aspect. I think that makes the whole thing fall apart. I have to talk about this in like classes like the 105 class. Because they all, well, you know, but the ice sheets on Denali in Alaska are, the glaciers are advancing in Denali, so therefore this whole thing's a bunch of crap. No, science is about putting together multiple pieces of information from multiple regions, and the expansion that you found a study that someone linked to on Facebook that said that these glaciers were advancing, that's fascinating. And probably there's some really interesting explanation about changes in the amount of precipitation on that mountain or whatever, but that's not the same thing as, and therefore there aren't problems with the cryosphere. Okay? That's an intellectual failing that we have to be careful not to make. But we have guidance from places like the IPCC to help us understand through their assessment reports what does the research mean. And what the IPCC is saying about the cryosphere is that it's virtually certain that, well, I'm sorry, that I'm going to go talk about the ocean first. It's virtually certain that the ocean has warmed between 1971 and 2010, and it's likely that it has been warming since the 1870s. The IPCC report got really bogged down. When you read that stuff, you noticed that they got very curious about the differences. They liked the global coverage once there were satellites in orbit starting in about the late 60s, early 70s, versus the much longer data record, but where there might have been problems with like the accuracy or the consistency or the homogeneity of the observations and so on. Virtually certain, though, is a huge number. I mean, if you look in there, what do they mean by virtually certain? I believe that's greater than 99% confidence. So anybody who tells you the oceans aren't warming, they are dead wrong. The oceans certainly have been warming since 1970. You have to have shared facts, right? Having different opinions about what that means and what policies you should act, that's a legitimate debate. But you have to do it in the context of shared facts, and there's no doubt about it. The facts say that the ocean has warmed. They also, you might remember from the readings, they also expressed their results and their interpretation of these papers in terms of confidence, where confidence is a measurement of the agreement or consensus between multiple studies. It's troubling when multiple studies tell you conflicting thing. But confidence for the period since 1970 is actually extremely high because all the studies using different methods and different data sets and different satellites and so on are all showing basically the same thing about what's happening in the ocean. It's very likely, according to the assessment report, I forget exactly how high very likely is. I think it's greater than 66% or something like that. Oh, there it is. I had it on the slide. I didn't realize it. 90% or higher. It's very likely that the mean rate of global sea surface change was about 1.17 millimeters per year between 1901 and 2010, and that it increased to 3 millimeters per year between 1993 and 2010. So not only is the ocean warming, the rate at which it is warming is very high, is increasing, and we have very good reason to think that. In fact, there's a 90% chance that this is correct. That's scary. All these climate change indicators are really scary. And this is all stuff comes from the observations and so on. Wait till you start seeing what like theory and modeling are going to be telling us about the rest of the 21st century, not to mention like the kinds of places your kids and grandkids are going to live out farther into the future. Oh man. All right. Let's answer a couple quick questions before we get done with this lecture. And again, this is one of the questions that actually did come from a past quiz. In the Arctic, sea ice extent peaks in A, September, B, December, or C, March. What time of year is the greatest extent of sea ice over the Arctic? Make a choice from those three options, get a little feedback before you go on to question 6.